Okay, so I'm Jordan Logan. I'm a dev tech engineer at AMD, and I've been working around with Vulkan for more than a year now, and I'm here to tell you how you can manage memory in Vulkan. So, quick agenda of what I'm going to talk about here. Introduce you to the current challenges of managing memory in Vulkan, and then all the different memory types that you'll commonly see out there. Unfortunately, this is mostly going to be about desktop GPUs since that's what I work with the most. There's also a bunch of tips and tricks you can do to get quite a bit of extra performance out of Vulkan and even reducing your memory usage. And there's some libraries out there that you can use to reduce the amount of work you have to do or even just get running. So real quick introduction to what the current issue is you'll run into with Vulkan is Vulkan. So with previous APIs, just a little history here, all you have to do to get memory on the GPU is just call create resource with a description of resource, and the driver handles all the work for you. But in Vulkan, we've moved that up to the application to do this, since we're a much lower level API, so you have to manage the memory on your own. So a bunch of responsibilities were moved to you. These responsibilities include managing the memory type and types, their sizes and alignments, make sure that you actually have the correct addresses, and you also have to do any sub-allocations of blocks. So you have to go through this, and then finally, after you have your memory blocks, you can actually start binding addresses to your memory. One of the questions we get a lot is, why do you actually want to do this? In previous generations of APIs, the driver was happy to do this. And that is because you know your application much better than the driver does. So you can actually achieve a much smaller memory footprint using this. And even you can optimize your application for the specific platform you're running on based off of its memory architecture. And there's a whole lot of new techniques you can do to improve your, that you couldn't do with previous APIs, one of which is actually aliasing your resources that you have, like your render targets, with future render targets and reduce the memory there. So let's start off by talking about the memory types. Now, some quick terminology is that in Vulkan, you have memory heaps and memory types. The heaps are actually your physical memory, like your VRAM and your DRAM, while a type is simply describing the actual properties of that memory and how it acts, and also which heap that type of memory uses. I'm going to show you real quick a bunch of different GPUs out there. So first off, we have Intel, which has a single heap and 2 types. And then on NVIDIA, we have 2 heaps with 11 types. And finally, at AMD, we have 3 heaps with 4 types. So there's a lot of different configurations you can see from the different memory. So you have to account for all of this. And deciding which memory type can actually be quite difficult. Some resources can only go into certain memory types while others can't. And also, you need to know, deciding which one is the best performance for your usage depends. Each memory type has a flag associated with it. And using this flag, you can actually determine the properties of this. So I'm going to talk real quick here about the different types of memory you'll commonly see. Your device local memory is what you'll be working with the most. This is your VRAM, and you have no access from the CPU, so you have to use transfer commands to get your memory here. And the type of resources you want to place in this are any high bandwidth resources. So render targets, depth targets, storage, image, and buffers have the largest impact by going into this memory, followed up by anything that doesn't actually change that often to minimize number of transfers. Transfers like your textures and vertex and index buffers. The next type of memory we have is the host visible. This is typically your DRAM if you're working on a desktop. And you can map this so you can write directly to it from the CPU. If you're working on a desktop GPU, a dedicated GPU, you'll have to, these reads will be across the PCI Express press, so there's some added latency to that. And the typical usage for this memory is setting up your staging buffers before you transfer them over to the device local. Other uses, although it's not exactly the best, but you can actually do your write once on CPU, read once for resources, like constant buffers in here, since the GPU caches all the results as it reads them in. But you should make sure you measure that in your application and make sure that isn't actually a huge amount of latency hit. You'll also use this memory for spelling, if you ever spell a device local, so that your application can keep running. Needless to say, you should probably never put any high bandwidth resources in here because of the increased latency. And this memory is by default uncached, so reads from this will be quite a bit much slower than what you're typically used to, and your writes could be write combined, depending on the driver and operating system. The next type of memory is actually something you can only see on AMD, right? AMD, and it's a 256 megabyte heap. It's that third heap we had earlier, and this is again, this is VRAM, so it's on the GPU, but it's actually been mapped to CPU addresses, so you can directly write to this from your CPU, and you don't need to do any explicit transfers or anything. There's a lot of uses we found for this, but like the most obvious use is your constant buffers or anything you're constantly updating. One thing you do have to realize is that since this memory has been carved out of your normal device local heap, you could actually severely reduce that heap size, especially on lower end cards where there's only 1 or 2 gigs. This is a significant portion. So we should just also using this heap and memory type for that as a backup to that. You also got to be careful as the driver will use this heap for implicit resources like descriptors and such. So you do not want to use the whole heap, otherwise you'll just spill into your device host visible memory. And as with the previous one, this is also uncached and could have write combined. With that, even worse is it's across PCI Express bus, so reads are very slow from this memory. Finally, we have the host visible host cache. This is system RAM. You'll find this acts just like the memory you're used to in like C and C++ with reads and writes cached. The GPU can also read this memory and snoop the CPU cache. There's some added latency to that. And you'll typically want to use this for any readback resources that you need fast reads from the CPU, or even if you're doing random access on them. And since the GPU can write to this, you can even skip transfers. Okay, so those are the 4 typical types you'll see. We actually have AMD APUs, and these are a little weird, so I wanted to put this last. First off, you'll notice that it has the exact same heap and type structure as our dedicated GPUs, and that's because we actually do get some faster, certain portions of the memory is actually faster. One thing you should note, though, is that the device local heap could actually be reported as being 0 bytes on some configurations. So the memory is actually really unified. It's all coming from your DRAM, but there is a portion of that memory that is much faster, and we report that back as the device local. And this memory, you want to put all your depth and render targets in there, as they see the largest benefit from the increased speed. Now, because of this, the difference between host visible and device local is much smaller compared to dedicated GPUs. You want to make sure you don't start using a lot of streaming in your resources. You'll want to, so for your streamer, I suggest is that you also count the sizes of the host visible as your maximum memory. And then always just fill your resources starting with device local, then your device local host visible, and finally you spill into system RAM. So those are all the different memory types that you'll commonly see on the desktop GPU, on desktops. So next I wanted to talk about all the different ways you can actually improve your memory allocation, apart from just selecting the most optimal memory type. First off, and just quick overview of this, because this is very important, is that Vulkan allocates memory in memory blocks. In older APIs, the resource was the owner of the memory, and you could not control where you place your memory. But in Vulkan, you allocate the blocks yourself, and then you decide where the resources go in that. So a single memory block can actually have many resources in it. And this allows a lot of interesting techniques you can actually now add. You can start to try to pull all your similar block memory resources together that have the same alignment and size to try and reduce the amount of wasted memory due to alignment. Or you can just pull all your object resources together to make it to simplify streaming in new resources, since they'll all be in one contiguous range. Now, there are some things you have to be aware of with the new memory block architecture. One is that you have to sub-allocate, otherwise you'll run into a lot of issues. For one, there's a very small limit on the maximum number of allocations you can do. If our driver reports back 4,000 of them, and so you cannot do a single resource per memory block. So our recommended solution to this is to always use much larger blocks. 256 megabytes is the one that we have found to be a good default size, unless you're on a small heap. And then you break that up, and then you just sub-allocate your resources from this. Also, you should note that these allocations are very slow. They're equivalent of doing a virtual allocation in Windows, as it goes down to a pretty low level. And so you should definitely not do this during any places where a hitch in amount of frame time could cause issues. The next thing I want to talk about here is that overcommitment. It's always going to be an issue you'll have to fight with, as you're always going to have more resources than you have like device local memory. So what happens when you go over the limit, it actually depends on the driver, as the allocation may just fail and report that it's out of memory, or the allocation will just succeed and just move over to system RAM for that allocation. But another issue, a similar issue to this, is that your blocks may be migrated to system memory anyway, since you're not the only application running on the PC, and the operating system will need to move memory out to run other applications. And using these blocks, of course, is much slower, and you'll notice it's on hitch and frame. So it's best to not use the 100% of any of the heaps, just to make sure there's room for other allocations or any implicit resources like swap chains actually do go towards your memory budget, even though you don't allocate the memory for those. So we recommend that you leave at least 20% of the device local memory available and around 33% of the device local host visible memory for all your implicit resources, and just to leave a little room for application other programs to run. Eventually, we need to get some data into your memory, so we'll just move on to the topic of mapping. Now, unlike previous APIs, there is no versioning, automatic versioning of resources as you allocate and map them. So you have to do that yourself. But with this removed of the requirement of versioning, you can actually just leave your resources persistently mapped throughout the whole frame, and even when you submit and present, with a couple of exceptions you should be aware of. The first one is that on the device local visible heap I talked about earlier, and that type, on older versions of Windows 10 predating Windows 10, that if you had that heap, any memory of that memory mapped, when you call it submit or present, the operating system would have to migrate that to system RAM due to some requirements of the old Windows display driver. Another thing you should note is that if you're using a lot of debugging tools, the more memory you have mapped during these present and submit calls, the slower they will be and the more unstable they'll be. This is due to the fact that they have to actually track more memory, and they might not actually catch all of the writes you do. The other way of getting data to your queues is using transfer commands. You can use these on any queue that supports the transfer bit, but there's a special queue that you'll find on dedicated GPUs that only supports the transfer bit, and that is the transfer queue. And this queue, this is the most underutilized queue in Vulkan. Very few people actually use it, and it is extremely powerful. Since it is completely asynchronous to the graphics hardware, it doesn't use any resources from that you would need during rendering. You can actually run this in the background and actually use it for things such as texture streaming, or even some more creative uses. Like one we've found is that you can use this to defragment your memory by just having it in the moving memory from one block to another block in the background, and then as soon as that resource is done, you can just update the frame, the descriptor for the next frame, and reuse that memory later. A few things you should note about the transfer queue. One is that you'll typically find that there's more than one. On the RX 580, it actually reports having two queues. So you can do two things. You can actually use this to simplify logic a lot. Like you can use one queue just for defragging all your memory, while the other one is streaming resources or textures. Another thing that you should definitely be careful about is that if you do a GPU to GPU copies on the same GPU, the transfer queue is not actually very fast at doing that. It's extremely fast at crossing PCI Express, not so fast on that. And also with the added synchronization, it might even slow down, cause even more issues for you. So on those, you want to use the graphics or compute queue to do those copies. And one thing this has gotten me quite a few times is that if you don't respect the copy queue's granularity is much more coarse than the graphics or compute queue, you can run into a lot of issues. I've seen corruptions of data, not successfully copying the data, crashes, or my favorite one that I have to debug is the entire queue is deadlocked and will never pass that copy. Thankfully, by spec requirements, full sub-resource copies, though, will always succeed, and you don't have to respect the granularity within. Next thing I wanted to mention is aliasing. This is a new feature that you can use thanks to the Vulkan's block allocation method, where you can just bind the same address to multiple resources. And as long as you don't use them simultaneously, it's fine. We've heard of savings up to 300 megabytes by just aliasing render targets with editor render targets or even storage images. And one thing you need to be careful here is that there's typically some metadata that is added to that resource, and if you could overwrite that, so you have to always go back to uninitialized layout whenever you switch what the memory is using. Once you actually experiment a lot and know exactly what you're doing and what the metadata when it will get corrupted or not. So I'm going to go a little bit off topic from memory here and just talk about some resource creation. So these are optimizations we typically tell people to do. First off is that tiling linear is very bad for performance, and that instead you should always use the optimal tiling format. And when you're doing your copies to and from the image, you should always use the VK copy image from buffer and vice versa. I actually found that the code for doing those copies is much simpler than just using a tiling linear image for my staging buffers. Next up is usage bits. If you set every usage bit, it will disable a ton of optimizations that the graphics card can do and the driver can do. So you should always use the usage bits that you absolutely need and not set all of them. A similar thing is that the concurrent flag is on render targets and depth targets, disables quite a few of our optimizations for that. And it's best just to use an exclusive mode and do explicit queue transfer ownership barriers. And finally, last one is please use the image format list. If you need mutable formats, just specifying the mutable format bit. The driver immediately assumes that every single format is possible and you will use it. And if you're doing that, I'm really curious what you're doing. Okay, so there's a lot of work with actually getting Vulkan memory management up. So one of the things we did at AMD is we actually created a library you can use that's open source. It's known as the Vulkan Memory Allocator. It's quite simple, actually. It was designed to be easy integration with a single header and to make sure it matches with the flow of Vulkan. And it's already been used in a few AAA titles, and I find that it's a great starting point if you're just like trying to get your engine up and running in Vulkan. You can just drop this in and worry about memory management later, or if you're just looking for some example code to write your own. So I'm just going to talk real quick about this. The main idea behind this is to pick the correct memory type based off of some usage flags that everyone was used to from previous APIs, and also to handle all that sub-block allocation. So I'll just show you some example code here. So this here is simply just creating a vertex buffer. So you fill out the create info buffer, and then you have a similar VMA allocation create info, and you just zero initialize this and set your usage. This usage flag will probably be familiar if you've worked in DirectX 11 with just GPU only. And then you call this wrapper function, create buffer, and it will do the whole flowchart that I mentioned earlier, where it creates the resource, it queries the API for the memory types, figures out the best memory type, and then sub-allocates the block and then binds it. So this is very similar to what you'd be used to if you're porting. One of the cool things that this library also does is that there's a bunch of helper functionality and debug. One of which is that it can just dump out every allocation you ever did and all the memory blocks into a JSON file. And then you can just put this JSON file through a script. This script is actually on the GitHub with the allocator itself. And this script will dump out an image that lets you look at your allocation. You can use this to quickly see if you're fragmented or if if you're fragmented or have memory blocks with low occupancy of memory. So in this one here, you can see that it is mostly filled with tiling optimal images and buffers. And there is some fragmentation, but not much. Okay, so in conclusion, just want to, the memory management has been moved from the driver up to you. And so now you have to do all that black magic that the driver used to do with memory. And so now it's a multi-step process and such. Also, all GPUs differ quite drastically between their different ways they actually handle memory. So you actually have to account for that in your engine instead of just allocating and hoping the API does the correct thing for you. But it's pretty simple to actually just keep the code very simple and follow some basic practices, and then you can actually get very optimal performance on a GPU. And of course, there's actually open source libraries to help you out with this. Here's some references if you guys want to take a look at these. There's quite a few articles by various IHVs, and my favorite resource is actually the Vulkan hardware database, since a lot of times I'll be asked to help debug on the hardware I don't own, but I can just go look up what its memory types and heaps are and what it supports. Thank you. So, any questions?
Does the AMD allocator is available on NVIDIA cards, or it's just specific to AMD cards?
Oh, the
allocator, memory allocator.
It works on NVIDIA too.
Okay, cool.
It's written generic enough that it should work on any vendor. If you have any issues, you should definitely file a issue ticket on the GitHub.
So one of the use cases that I generally don't see you guys tackle is that you always assume we're allocating small resources. So one of the use cases we have on our APIs, and I know other people have it too, is that we actually have super large resources that grow and shrink. So I know sparse resources are a thing in the API, but I know that is not super well supported across all vendors right now. So
yeah, it's currently not very well supported, and there's a lot of reasons for that you'd have to actually ask the people that work on that for reasons why. But I would probably just allocate a very large block, like dedicated block to that, and then just streaming into it as best as you can.
Yeah, so we do have a lot of these things. It gets to a point when you combine that with the restrictions where you're basically saying try to keep this amount of memory free. It kind of is not a scalable solution. If we actually need memory to be contiguous, then this is a very important use case in our view that should be tackled as a primary concern to not just assume all our resources can be sub-allocated. That's obviously one use case, but the other use case is also quite important. And the second thing is, I understand the spirit is now memory is your concern, but it also gets to a point when you say, oh, but the driver behind the scenes might actually allocate this in a different pool. So this kind of breaks the spirit a little bit. So maybe we need an interface where that information is given to us too, because that actually might translate into performance issues that we will have to tackle. So maybe there'll be some extension, or do we need to actually use OS-specific information to make those decisions, or should that be standardized in some way?
Yeah, I'd have to defer that question to Alon since he controls the API. Or
I think that'd be a good starter question for the discussion panel, because there's different views, and as you can see, this is where it comes to what can we say and what can we not when it is vendor specific. But I think the large allocation point is one that we should take back.
And definitely give us any feedback you have on Vulkan, as we also like to see that, and so we can actually prioritize what vendors want.
Yeah, sorry, I was a bit lost some point. When you do the memory allocation, you said it was two types. That's one can be mapped to the host, the other on the device memory. But for the device, like what kind of handle that you can use to, like, is there any API bound to transfer memory or?
Oh, transfer me?
Yeah.
So for transfers, it's just copying from one address to another.
Oh, okay.
So you just give it, so like VK copy buffer to image, you give it a buffer address resource handle and a image handle, and then it'll do the copy for you. Of course, there's some sub-resource.
So in that case, you have to actually have two memory allocated, then you can do the transfer, right?
Yeah. So typically you would map your a host visible page type, put all your data in there, and then you would call a transfer command with that as the source image, and then your destination image.
Okay, so just for confirmation, the basic unit in the memory allocation is that block.
Oh, sorry, say that again.
The basic memory management unit that you mentioned is the block unit.
Yeah.
Okay, thanks very much.